Hello. In this video, I will be solving problem 37 from section 12.2 of James Stewart's calculus. And the problem reads as follows. Three forces act on an object. Two of the forces are at an angle of 100 degrees to each other and have magnitudes 25 newtons and 12 newtons. The third is perpendicular to the plane of these two forces and has magnitude 4 newtons. And we're asked to calculate the magnitude of the force that would exactly counterbalance these three forces. Okay, so this is a physics problem, a nice one at that. And as is the case with any problem dealing with vectors, a good place to start is to always draw a sketch of what you're working with. Now what I'm going to do first is I'm going to draw a coordinate system since we're dealing with three-dimensional vectors, and we can get this hint by the fact that we're given a vector that's perpendicular to the plane of the other two, so we know we're working in 3D space. Let me get some coordinates. And now let's go ahead and sketch out what's going on with us with these vectors. So first, notice that we're given two of the vectors, two of the forces, at an angle of 100 degrees to each other on a plane. And because we've already drawn this coordinate system, it's really convenient for us to just make one of those vectors point in the direction of the positive x-axis. You'll see why in just a bit. It doesn't matter which of the two vectors we choose to have this property. Here, I'm going to let the 12 Newton vector point in the positive x-axis. So let's draw a vector here. Let's call this force 1. And we know that because the magnitude of the force is 12 newtons, this length is 12. I'll omit the units for now. Our second vector is, to make things convenient, all we need is that it's 100 degrees apart from force 1, but it'll be convenient for us to draw it such that it lies on the xy plane too. And once again, we'll see why this is the case once we start doing calculations. And so if this force is to have an angle of 100 degrees to the original force, then just extending these lines, well, the angle between the x and y axis is 90 degrees, so we're left with 10 degrees, which puts us roughly in this direction. Let's call that force 2. And this second force has a magnitude of 25. And we should probably draw out that the angle between these two guys is 100 degrees, because that was given to us. And finally, we need to address this third vector here, the one that's perpendicular to the plane of these two forces and has magnitude 4 newtons. Now, as it stands, the obvious temptation would just be to draw a vector pointing up, perpendicular to the xy plane, call that force 3, and just mention that force 3 has a magnitude of 4. But it doesn't have to be this way because they never told us in which direction or orientation this vector should point up. So equally well to us, we could have been handed the vector with the exact same magnitude, i.e. length, but pointing towards the negative z-axis. Now, we will see shortly that this doesn't actually affect any of our calculations, but it should be pointed out that a priori, we don't know that the vector f3 should be pointing up in the positive z-axis this way. It could very well be pointing down, and we're going to account for that once we give these vectors some coordinates. Okay, so now we have the first bit of the setup. And as a reminder, we want to find the magnitude of the force that would exactly counterbalance these three forces. Now, if the vector perpendicular to our first two were pointing up in this way, then we could estimate that maybe the vector that's counterbalancing probably points in that general direction, right? Towards the region of the XYZ plane where all three of the coordinates are negative. In contrast, if we were instead in this situation, then maybe the vector might look something like this instead. Just pointing in a direction such that it opposes the other three forces. But again, the fact that there's two possibilities for our force F, and you know what? Just for some bookkeeping, let me go ahead and label these vectors here. So this was our force 1. This was our force 3. And finally, our counterbalancing force. This is F. Okay. So if the force F is to counterbalance the other forces, then what that means is that when you add up, or I guess I can rephrase it this way. So recall that the net force acting on an object, and here it's good to note that our object here, we're taking it to lie in the origin. And so what it would mean for our force F here to counterbalance the other three forces in our diagram, and just to make sure we're clear, let me erase these other smaller possibilities. Precision. Let me just erase these for now, and I'll remind us of that possibility later on. Okay. So what it would mean for our force F to counterbalance these three forces here is, well, okay. If we have counterbalancing, like there's no net force, then the net force on the object, which is a vector, well, that's just going to be the zero vector. But by definition, the net force acting on an object is just the sum of all the different forces that act on that object, in this case, F, F1, F2, and F3. So the net force on our object is F plus F1 plus F2 plus F3. And so this gives us an equation relating all of our forces. F plus F1 plus F2 plus F3 equals the zero vector. Okay. Now, at this point, we can already solve for F if we just subtract all the other vectors to one side. This is negative force 1 minus force 2 minus force 3. And so to calculate what the length of our vector is, we just need to find some coordinates for these vectors, coordinate representations. Now, remember that we picked our force 1 to lie exactly on the positive x-axis. So the coordinate representation of F1 is as simple as it could be. F1, where I'm going to use a column vector to denote a vector and the components of the vector, sorry. This is just going to be the magnitude of our force 1. And then there's a 0 for the other two components because force 1 just lies on the x-axis. But what is the magnitude of force 1? Well, that's just 12. So this is 12, 0, 0. Similarly, F3 is going to be, well, now F3 only lies on the z-axis. It doesn't have any x or y components. So F3 will be 0, 0. And then for the z components, this is where we need to be careful about that possibility I mentioned earlier. You might remember I said that F3 doesn't have to be pointing up into the positive z-axis because all we're given is that it is perpendicular to the plane generated by these two vectors, F1 and F2. And that plane is the xy plane. So there's nothing stopping F3 from pointing down instead of pointing up as we've drawn it originally. And so to account for that, we need to add this plus or minus here, along with the magnitude of F3, which is 4. So just to illustrate what this means, and I could make it even better by making the minus sign red. If we take the plus sign here, we get this blue vector that points up to the positive z-axis. If we take the minus sign, though, we get this red vector that points down into the negative z-axis. Other than that, that's really the only nuance that we have to account for. And all that remains is to find components for F2, which is going to be a little trickier, just a little more work, because now F2 doesn't lie perfectly on any of our axes. To find the components of F2, let me go ahead and draw a sketch of just the xy plane, along with our vector F2. So again, the angle is 100 degrees, and our vector F2 points off into the negative x-axis and positive y-axis. To find components for F2, so first note that we already know that the components, the z components for F2 is going to be 0 because this vector only lies in the xy plane. See here? This has no z component, so we already know this last component will be 0. To find the other two components, let's break up this force 2 into its x components and then its y components, F2y. And all that remains is to figure out what the lengths of these two vectors are. If we can find those, then just making sure to add a minus sign to this length because we're pointing at the negative x-axis, we'll get the components x and y for F2. To do this, we can, well, okay. Clearly we have this right triangle. And so immediately our mind should jump to using trigonometry, and that's exactly what I'm going to do here. So first, by complementary or supplementary angles, I can never remember which one, these two angles have to add up to 180 degrees. So this angle must be 80 degrees. 180 minus 100 is 80. So the length of our y components, well, that's going to be the length of f2, which the length here is just the magnitude of f2, which we know to be 4. Oh no, 25, sorry. This is 25. So by trigonometry, the length of the y components is 25 times the sine of 80 degrees. Similarly, the x components is 25 times the cosine of 80 degrees. And again, reminding ourselves that we are pointing in the negative x-axis, we should add on this minus sign to the x component. And this gives us our coordinates for this vector. Let me just make a little more space. Cosine 80 degrees, 25 sine 80 degrees, and then we have 0. Okay, so now that we have our 3 component representations, let's plug them in to this equation right here and get components for f. So f is going to be negative, okay. F1 is 12, 0, 0. Just making that look like a 0. F2, we just found it to be negative 25 cosine 80 degrees, positive 25 sine of 80 degrees, 0. And then F3 is 0, 0 plus or minus 4. And again, you'll see why this plus or minus doesn't end up mattering in the end. So now just combining all the x, y, and z components respectively, we end up getting 25 cosine 80 degrees minus 12. So I did negative 12 plus negative negative turns into positive, 25 cosine 80 degrees, and I just rearranged. And then we subtract 0, which is just 0, so nothing to worry about there. The y components will be just negative 25 sine 80 degrees, because here we have 0, here we have 0. And finally, our z components will be minus plus 4, which is just another way of saying plus or minus 4. I decided to write it this way to emphasize that the negative flips the signs, but really you can equally think of this as plus or minus if you want. Now we're almost done. We have the components of f. The last thing we need to do, because we want the magnitude, and again, the magnitude is just going to be the length of this vector. Well, now that we have the components, we can just square them individually, add up the results, and then take the square root at the end. So this is for the x components. This is for the y components. And finally, we have the z components. And now you might already see why this minus plus doesn't matter at the end, because we're squaring at the end, and that's just going to make it 4 squared. So this is 25 cosine 80 degrees minus 12 squared. Likewise, we lose this minus sign here because we're squaring. And here the intense is to use a calculator, there's no hope to, or little hope, I should say, that's better. Little hope to evaluate this by hand. And so using a calculator, we end up finding that this is approximately 26.0924, or if we want to only keep it to the first decimal place, this is 26.1 newtons, remembering to add our units at the end. And if you look at the back of your Stewart calculus book for the 9th edition, you'll find that this is exactly the answer they give for the magnitude of this vector. Okay, that's it for this video. If there are any questions, please feel free to leave a comment. Otherwise, I will see you all in the next video.